Hi there. So this is the third and final part of the calculus crash course, and it's going to be on differential equations, solving differential equations. Now, we didn't say we were solving differential equations in the previous section, but you kind of were. You just didn't think about it from that perspective. Whenever I gave you the equation for lowercase f of x and said to find capital F of x, like the general antiderivative of the function lowercase f of x. That was solving a differential equation where you could think about like you're given the derivative and you are being asked to find its general antiderivative through the process of integration. So a differential equation is an equation that has one or more derivatives in it. The order of the differential equation is the highest derivative present in the equation. So like an equation that has a first derivative in it would be a first order differential equation. An equation with a second derivative in it would be a second order differential equation. We know that anti-differentiation, indefinite integration, and solving differential equations all imply the same process. Right? The process of finding the antiderivative. The differential equations we've seen so far have been explicit functions of a single variable. We're solving these equations meant getting back to the y equals or to the f of x equals. So given a derivative, finding its general antiderivative. So something like this. Like if we wanted to solve this equation and find its general antiderivative, we can just think about integrating 3 over 2 minus x. And that would be getting us back to y equals. So y equals would be equal to the integral of 3 over 2 minus x dx. This would require u substitution. So we'd let u equal to 2 minus x. Du over dx would be negative 1. So negative du equals to dx. We can pull out negative 3, right? Pulling out the constant, 1 over u du. And then when we integrate 1 over u, that would be negative 3 times natural log of absolute value of u plus c. And finish substituting what we let u equal to back in. There we are. That would be our general solution of that differential equation. That would be our y equals. Now, you are oftentimes asked to find a particular solution using an initial condition. The initial condition is just a point that lies on the graph of the particular solution that you're looking for. So you use that initial condition, plug in those values, and solve for what C would be, like what the particular value of C would be that would give you the particular solution. So to find the particular solution in this case that has the initial condition of y equals to 0 and x equals to 1, we will replace y with 0. And we will substitute 1 in for x. So this becomes natural log of 1, which is 0. So C actually just ends up being equal to 0 in this case. So the particular solution with the initial condition listed would just be negative 3 natural log of absolute value of 2 minus x. So some differential equations do not necessarily have just dy over dx equals to some rule in terms of x. Some more complicated differential equations might require this method referred to as separation of variables. And any differential equation that can be written in this form, which don't get too worried about this form, can be solved using separation of variables. And the separation part goes along with the method, right? So when you are using separation of variables, it means that you're getting all of the y terms on one side of the equation with dy and all the x terms on the other side of the equation with dx. So, and then you can integrate in order to solve. So like this equation is dy over dx equals to x over y. So since it's dy over dx equals to a rule that's in terms of x and y, we cannot just integrate x over y with respect to x. Like you can't do that. What we can though do is rewrite this as y dy equals to x dx. So thinking about multiplying y on each side of the equation and then multiplying dx on each side of the equation. So now we have separated the variables. We can now think about integrating. Those are yucky integral symbols. We can now think about integrating each side of the equation here. When we integrate the left-hand side, that would be 1/2, with respect to y, 1/2 y squared. And you could think about a plus c, but we're going to do the plus c on the other side. Like you don't need to have plus c on both sides. And then 1/2 x squared plus c on the right-hand side when you integrate with respect to x. And then from here, like we could multiply by 2 on both sides of the equation to isolate the y squared. When we do that, so when we multiply by 2, when we distribute the 2 to the 1/2 x squared, that'll become x squared. When we distribute the 2 to the c, you can almost think of it like the c, that arbitrary constant, is absorbing the 2, because 2c would just still be an arbitrary constant, right? So we can actually just write plus c. And then from here, if you wanted, you'd have to have 2 rules to have just y equals. You'd have y equals to positive square root and then y equals to negative square root. Or you can just leave as is. Like this would be the general solution to that differential equation. If you would like, you can try this one on your own. Pause the video and then check your answer. Again, because this is not dy over dx equals to in terms of a rule in terms of just x, you can't just think about integrating. So we're actually going to use separation of variables. To do this, I'm going to think about dividing by y on each side. So I would have 1 over y dy equals to 2/3 and multiplying by dx on each side dx. So now I can integrate. When I integrate y, I'll get natural log of absolute value of y equals, integrating with respect to x, 2/3 x plus c. And then from here, we usually want to get in the form, like at least in AP Calculus, like we usually want to get to the form y equals. So in order to do that, we're going to use our properties of logarithms. Right? Another way to write this, so rewriting this in exponential form, right now we can think of this in log form, would be e to this power equals to absolute value of y. And then using an exponent property, the right-hand side here can be written as e to the c times e to the 2/3 x. Now, e to the c is also just going to be an arbitrary constant. We can just call that c. And then to get rid of the absolute value bars, we have to take into account that whatever is inside of the absolute value bars could be positive or negative. So this would be plus or minus e to the c times e to the 2/3 x. But this entire plus or minus e to the c is again just an arbitrary constant. So we can actually just write this as y equals 2c times e to the 2/3 x. And that's it. That would be our solution. Okay, let's check out this one. So this one, we're finding a particular solution that would pass through. This is the point -2, 1. This is like using function notation and calling your function y. Y prime can also be written as dy over dx. Remember, they mean the same thing. So it might be helpful for us to rewrite this differential equation as y times the quantity x plus 1 plus dy over dx equals to 0. And remember, our goal here is going to be to get all of the y's on one side and dy and all the x on the other side of dx. We're kind of stuck the way that it's written as is. So I'm going to try subtracting y times the quantity x plus 1 from both sides. Okay, and then now I can divide by a negative y and multiply by dx on both sides. So I'd have the quantity x plus 1 dx. And now we have separated the variables. And this step's really important to show. And you can integrate. So this would be negative, I'm going to put parentheses around there. So negative ln of absolute value of y equals to 1/2 x squared plus x plus c. And I'm going to divide out that -1. Again, we're trying to get to the y equals. Now you can technically solve for c at any step. You just need to make sure you're substituting what you get for c back in and then finish solving for y. But I'm going to try and get all the way to y equals before I solve for c. That's just my preference. I don't need to write minus c. That can just be plus c. Think of the c as absorbing that -1. And then rewriting in exponential form, e to this whole power is equal to absolute value of y. Okay. And then to split this up so that we can get that constant out of the exponent position. Sorry. That would be e to the c times e to the negative x squared over 2 minus x. So that's just a constant. And then again, we could think about the plus or minus e to the c times e to the negative x squared over 2 minus x. This is just a constant. So we can just write, some texts will rename that like capital K, like choose a different constant. I'm just going to call it capital C. So that's the general solution and to this differential equation, but we want to find the particular solution that has this initial condition. So where x is -2 and y is 1. So substituting 1 in for y, remember we're solving for c, and then was it -2? Yeah, -2 for x. Okay, so then that ends up being -2 plus 2. So e to the 0th power, which is just 1. So c actually ends up just being 1 in this case. So that we're not done. The particular solution would be y equals, c is 1, so it would just be e to the negative x squared over 2 minus x. That would be the particular solution. Oh, didn't mean to erase that. That would be the particular solution to this differential equation. This is something that we cover towards the end of the year, second semester, but it may come up sooner in AP Physics. Okay, so that's the idea behind solving differential equations. When you're solving a differential equation, you're finding the antiderivative, whether it is the general antiderivative of the differential equation or if it is the particular solution. But to find a particular solution, you need to have an initial condition, which is just a point that lies on the graph of that particular antiderivative. Okay, let me know if you have any questions.